Namaste, and welcome to Dr. Vikrant Verma classes. I'm thrilled to have you join me today as we embark on an exciting journey into the world of organic chemistry. Now, I know what you might be thinking. Organic chemistry? That sounds intimidating. But trust me, my friends, it doesn't have to be. In fact, once you understand the fundamentals, it becomes a fascinating puzzle waiting to be solved. In this video, we're going to break down the essentials of organic chemistry reactions in just 10 minutes. You heard that right, just 10 minutes to grasp the basics. Whether you're a student struggling with these concepts or simply someone with a curious mind, this video is tailored for you. We'll cover the most important reaction types, delve into their mechanisms, and illustrate their significance with real-world examples. My goal is to make organic chemistry as clear and engaging as possible, so you walk away feeling confident and eager to learn more. So if you're ready to unlock the secrets of organic reactions, buckle up and let's dive right in. Let's kick things off with substitution reactions. Imagine you have a group of friends, and one friend wants to switch places with another. That's essentially what happens in a substitution reaction. More formally, it involves the replacement of an atom or a group of atoms attached to a carbon atom with another atom or group. Think of it like swapping ingredients in a recipe to create something new. Now, within the realm of substitution reactions, we have two major players, SN1 and SN2 reactions. Don't let the names intimidate you. SN1 stands for substitution nucleophilic unimolecular, while SN2 stands for substitution nucleophilic bimolecular. I know these terms might sound like a mouthful, but they actually tell us a lot about how these reactions occur. In SN1 reactions, the unimolecular part is key. It means that the rate of the reaction depends only on the concentration of one reactant, the molecule undergoing substitution. Picture this. A molecule decides to break up with its attached group, creating a vacancy. Then, another group, called a nucleophile, which is attracted to positive charges, swoops in to fill that vacant spot. It's like a game of molecular musical chairs. On the other hand, SN2 reactions are a bit more direct. Here, bimolecular means that the rate depends on the concentration of both the molecule undergoing substitution and the incoming nucleophile. It's a one-step process where the nucleophile attacks the molecule from one side, while the leaving group departs from the other side. Imagine a well-coordinated dance where partners switch places seamlessly. Now, let's look at an example to solidify our understanding. Consider the hydrolysis of alkyl halides. An alkyl halide is simply a molecule where a halogen atom, like chlorine or bromine, is attached to a carbon atom. During hydrolysis, water acts as the nucleophile and attacks the carbon atom bonded to the halogen. In an SN1 reaction, the halogen would first leave, creating a positively charged carbon atom called a carbocation. Then, water would attack this carbocation, leading to the formation of an alcohol. Conversely, in an SN2 reaction, water would attack the carbon atom while the halogen is still attached, leading to the displacement of the halogen and the formation of the alcohol. The choice between SN1 and SN2 pathways depends on factors like the structure of the alkyl halide, the strength of the nucleophile, and the solvent used. For instance, tertiary alkyl halides, where the carbon atom bonded to the halogen is attached to three other carbon atoms, are more likely to undergo SN1 reactions due to the stability of the carbocation intermediate. Understanding substitution reactions is fundamental in organic chemistry, as they are involved in numerous synthetic transformations and biological processes. From the synthesis of pharmaceuticals to the reactions occurring within our bodies, substitution reactions play a vital role. Now that we've grasped the concept of substitution, let's move on to another important class of reactions, addition reactions. As the name suggests, these reactions involve the addition of atoms or groups of atoms to a molecule, specifically to unsaturated compounds containing double or triple bonds. Imagine two dancers holding hands, representing a double bond. An addition reaction would be like another dancer joining in, breaking one of the handholds and forming two new ones. This is exactly what happens in these reactions. A double bond is broken, and two new single bonds are formed. One of the most common examples of addition reactions is hydrogenation. You might have heard of this term in the context of food chemistry. where unsaturated fats are converted to saturated fats through hydrogenation. Chemically, hydrogenation involves the addition of hydrogen, H2, across a double or triple bond. Let's visualize this with the help of an example. Consider ethene, the simplest alkene, with a double bond between two carbon atoms. When ethene undergoes hydrogenation, two hydrogen atoms are added across the double bond, resulting in the formation of ethane, an alkane. This process typically requires a catalyst, such as platinum or palladium, to speed up the reaction. The significance of hydrogenation extends far beyond food chemistry. It plays a crucial role in various industrial processes, including the production of margarine, polymers, and pharmaceuticals. In the petrochemical industry, hydrogenation is used to convert unsaturated hydrocarbons into more valuable saturated hydrocarbons. Another important type of addition reaction is halogenation, which involves the addition of halogens, such as chlorine, Cl2, or bromine, Br2, across a double bond. This reaction is often used as a test for unsaturation. If a solution decolorizes bromine water, it indicates the presence of double or triple bonds. Addition reactions are incredibly versatile and form the basis for countless chemical transformations. They are essential for the synthesis of a wide range of organic compounds, from simple molecules like ethanol to complex polymers with specific properties. Our final stop on this whirlwind tour of organic reactions takes us to oxidation-reduction reactions, or redox reactions for short. These reactions involve the transfer of electrons from one molecule to another. Think of it like a game of hot potato, but instead of a potato, we're passing electrons around. In organic chemistry, oxidation is often associated with the loss of hydrogen atoms or the gain of oxygen atoms, while reduction is the opposite, the gain of hydrogen atoms or the loss of oxygen atoms. Remember the acronym OIL-RIG. Oxidation is loss of electrons. Reduction is gain of electrons. One of the most common oxidation reactions is the conversion of alcohols to aldehydes or ketones. Alcohols are organic compounds containing a hydroxyl group, OH, attached to a carbon atom. When an alcohol is oxidized, it loses two hydrogen atoms, one from the hydroxyl group and one from the carbon atom attached to the hydroxyl group. Let's take the example of ethanol, the alcohol found in alcoholic beverages. When ethanol is oxidized, it forms acetaldehyde, which is further oxidized to acetic acid, the main component of vinegar. This two-step oxidation process is what gives vinegar its characteristic sour taste. The oxidation of alcohols to aldehydes or ketones has numerous applications in organic synthesis. Aldehydes and ketones are important intermediates in the production of various chemicals, including pharmaceuticals, fragrances, and dyes. On the other hand, reduction reactions in organic chemistry often involve the addition of hydrogen atoms across a double bond, or the conversion of a carbonyl group, C=O, to an alcohol. For example, the reduction of acetone, a common ketone, produces isopropanol, commonly known as rubbing alcohol. Understanding redox reactions is crucial in organic chemistry as they underpin countless chemical transformations, both in the laboratory and in nature. From the breakdown of food molecules to generate energy in our cells to the industrial production of fertilizers and polymers, redox reactions play a ubiquitous role. Congratulations! You've just mastered the essentials of organic chemistry reactions in record time. We've journeyed through the fascinating world of substitution, addition, and oxidation-reduction reactions, uncovering their mechanisms and significance. But this is just the beginning of your organic chemistry adventure. To truly appreciate the power of these reactions, let's consider a real-world example, the Grignard reaction. This Nobel Prize-winning reaction involves the addition of a Grignard reagent, an organomagnesium compound, to a carbonyl group, forming a new carbon-carbon bond. This versatile reaction is a cornerstone of organic synthesis, enabling the creation of complex molecules used in pharmaceuticals, agrochemicals, and materials science. From developing life-saving drugs to designing new materials with tailored properties, organic reactions are the driving force behind countless innovations. They hold the key to addressing global challenges in areas like renewable energy, environmental sustainability, and healthcare. As you continue your exploration of organic chemistry, Remember these quick study tips. First, recognize patterns in reaction mechanisms. Just like recognizing recurring themes in a good book, identifying patterns will deepen your understanding. Second, focus on electron flow and functional groups. Electrons are the driving force behind chemical reactions, and functional groups dictate how molecules behave. Finally, practice with real-life examples to strengthen your understanding. And here's a fun challenge for you. What do you think would happen if you reacted an alkene with water in the presence of an acid catalyst? Let me know your predictions in the comments below. Keep that curiosity alive, my friends. Namaste, and until next time, happy learning.